induced settlements. If we see past history, soil liquefaction has been major cause of damage to soil structures, lifeline structures, building foundations during past earthquakes. He has already shown you some pictures, so I have not included those pictures again, and clearly poses significant threat to the integrity of structures and other facilities during future earthquakes. Evidence of occurrence of liquefaction has been reported from large number of earthquakes. Shonai 1894, Assam, Kanto, Bihar, Pukoi, then Assam 1950, Jaltipan, Chile. But it was only after earthquake at Niigata and Alaska in 1964 that the problem of soil liquefaction was investigated in greater detail, and efforts have been increasingly directed towards the development of methods of evaluating the liquefaction potential of soil deposits. Only after 1964 earthquake, people started working towards liquefaction, detection of liquefaction, why liquefaction takes place and how to measure it. Soil liquefaction, as already explained, that describes the behavior of soil that when loaded suddenly suffer a transition from a solid state to a liquefied state, or having the consistency of heavy liquid. Liquefaction is more likely to occur in loose to moderately saturated granular soils with poor drainage, such as silty sands or sands and gravels capped or containing seams of impermeable sediments. If we see this picture, you can see boundaries, these boundaries. If soil is between these boundaries, that is most liquefiable soil. If it is within this, it is most liquefiable. This is also liquefiable. If it is beyond that, if your soil is not in that part, beyond that these boundaries, then there are minimum chances, no chances you can say of liquefaction. Now, evaluation of liquefaction potential. First, based on SPT, standard penetration test. All of you must be aware of standard penetration test. We calculate N value. We give number of blows of 65 kg hammer and penetration for 300 mm penetration through a free fall of 75 centimeters or 750 mm. Number of blows are counted for 300 mm penetration, that is N value. So N value is recorded. Here it is written N160. N160 because there is energy loss when hammer energy is given, some energy loss is there, approximately 60% energy remains that is actually applied. So that's why they have named N160. So actually N160 is observed N value. So N160 is then Nm is observed value actually. Nm is observed value. Then we apply some corrections to that, we get N160. N160 is corrected N value. So N160 is Nm into Cn, Ce, Cb, Cr, Cs. These are correction factors for overburden resistance, correction factor for hammer energy, correction factor for borehole diameter, correction factor for rod length, correction factor for samplers with or without liner. Because overburden changes as we go down, overburden changes. As we go down, more overburden is there. So we rationalize the values, because where overburden is more, there you will get more confinement and higher N value. So we reduce those values to some extent. Okay. So different corrections. This I already told you that why 60% we take, because actual energy transferred is 60%. Then correction factor for overburden pressure. For overburden correction factor, we multiply with Cn. Cn is Pa upon sigma V0 dash raised to power 0.5. Pa with 100 kPa we take 100 kPa and sigma V0 dash effective overburden pressure at the depth of SPT. Suppose SPT is conducted at 5 meters, then within that 5 meters, considering the water table, we convert gamma to gamma submerged wherever required. So that's why effective, not total. Effective overburden pressure at the level at which test was conducted. For other corrections, this table is used. We will borehole diameter correction. If diameter is 65 to 115, then correction factor is 1. For 150 it is 1.05. For 200 mm it is 1.15. Similarly, energy ratio for safety hammer, for donut hammer, which hammer is used. Accordingly, for different types of hammers, these correction factors are applied. For rod length, if rod length is 3 to 4 meters, test is conducted within 4 meters, then for those values correction will be 0.75. Then for values of SPT N values which are between 4 to 6, correction factor is 0.85. Like this, these correction factors will be applied. Similarly, sampling method. Now then, this N160 which you have calculated, then it is converted to N160 for clean sand. In our soil, fines may be more than 5%. If fines are more than 5%, then it is not clean sand. If fines are less than 5%, then we consider it clean sand. We convert our value to clean sand value, because curves which are available, which are reliable, considered reliable, they are for clean sand. So we convert our N160 value to N160 CS. This N160 CS for clean sand. So alpha plus beta N160. Alpha is calculated, this coefficient is calculated as exponential 1.76 minus 190 upon Fc square. Similarly, beta 0.99 plus Fc raised to power 1.5 over 1000. This Fc is fines content in percentage. This is in percentage. If fines in our soil, they are say 35%, then Fc will be 35, not 0.35 in this equation. So, then 30 Fc will be in percentage. We will calculate alpha and beta, then substitute the values of alpha and beta in the equation. You will get N160 CS. So, N160 CS you will calculate. Then curves are available. Those curves I will show you first. These curves are available. From these curves, this curve is for fines content less than equal to 5%. Less than equal to 5% means clean sand. So we will see this curve. This is cyclic stress ratio, and here we have N160. On these curves it is written N160. We will see this curve. So whatever value you have calculated N160 CS corresponding to that value, N160 CS value corresponding to N160 CS value, we see this curve, whatever value you will get, that is cyclic stress ratio. This is cyclic, actually this is cyclic resistance ratio. Cyclic resistance ratio. Though it is mentioned on these curves, this CSR, this is CRR. Okay? You will consider it resistance. And secondly, these values are for earthquake of magnitude 7.5. This is for earthquakes of magnitude 7.5. If you are expecting earthquake of different magnitude, then correction is applied. Magnitude scaling factor, that I will let you know. This magnitude scaling factor. CSR M over CSR M equal to 7.5. That ratio is magnitude scaling factor. So magnitude scaling factors are there. Suppose you have considered earthquake in that particular area for which you are going to calculate liquefaction potential. If expected earthquake is say of magnitude 7.5, then that magnitude scaling factor is 1. If expected earthquake is 8.5, then magnitude scaling factor is 0.89. Similarly for others. So accordingly you will modify the value of CRR. Okay. Now others value cyclic stress ratio. That was cyclic resistance ratio which you have calculated from the curves. Now you will calculate cyclic stress ratio. Cyclic stress ratio is calculated using this equation 0.65 sigma V0 A max upon sigma V0 dash into RD. RD is stress reduction coefficient. Stress reduction coefficient that accounts for this is stress reduction coefficient that accounts for the flexibility of soil column. For example, RD equal to 1 corresponds to rigid body behavior. So that depends upon flexibility. So sigma V0 and sigma V0 dash. What is sigma V0? Overburden pressure, total, and sigma V0 dash is effective. So if you have conducted the test at say 6 meters, then water table is let us suppose at 4 meters. So up to 4 meters, gamma into 4, if soil is same, then beyond 4 meters, it will be gamma submerged into 2 meters. So like that you will calculate this sigma V0 dash, and this sigma V0 is total. Here we will not consider that effect of submergence, we will always take total. If above the water table it is total, if below the water table then gamma saturated. Total is gamma saturated below the water. So 0.65 sigma V0 A max acceleration, expected acceleration in that particular area, let us say earthquake of 0.25 G is expected. If earthquake of acceleration 0.35 G is expected. So this A max will be 0.25 or 0.35 or 0.3 like that. So sigma V0 you can calculate. You have performed SPT. After performing SPT you will get N1 and you will get NM measured values. Then convert to N160. Then N160 will be converted to N160 CS. Then you can see the curves. From the curve you can calculate CRR. Now you have to calculate CSR, stress. For that sigma V0 you will calculate at the same level at which SPT was conducted. At that level sigma V0 and sigma V0 dash will be calculated. A max expected earthquake acceleration 0.35 or 0.3 G, 0.25 G like that. So we will take in terms of G. G we will not write in this equation. A max, if earthquake is 0.3 G, we will take A max equal to 0.3. Okay. Then RD stress reduction factor. Stress reduction factor we can take from these equations. Stress reduction factor we can calculate if Z is less than equal to 9.15, then this equation. If it is between 9.15 to 23, then this is the equation, and so on. Like this we will calculate RD. Now everything we have in that equation. So from that you will calculate CSR. Now you have both CRR and CSR. RD you can calculate from curves also. That table is also given after conversion. Now we will compare CRR and CSR. If your resistance ratio is higher, if resistance is more, naturally factor of safety is more than 1. So if factor of safety is more than 1, then earthquake is liquefaction is not expected. If ratio is less than 1, then liquefaction is expected. Okay. So you will calculate factor of safety CRR upon CSR. I think clear. For example, let us suppose we have n value of 12 and gamma value is given to you. Water table is also given somewhere at 3 meters. We are earthquake of 6.75 magnitude is expected. We are to maximum ground acceleration is expected in that area 0.35. We calculate factor of safety against liquefaction. So we will calculate sigma V0 dash. Here we have taken minus gamma W submerged below the water table. So 21 minus 10 we have done. Gamma saturated minus gamma W. So let us say this is 76.5. Now sigma V0 total average earth pressure. So 20 into 3, this will be 21 into 1.5. Total we will take, so it's in 91. Now similarly stress reduction factor from this equation, we will calculate that is, let us say 0.965. CSR 0.263 from the equation we can calculate. Equation which I have shown, from that you can now calculate CSR. Now next is CRR. For CRR N160, Nm is given to you 12, that is given in the problem, and Nm 12, then these correction factors will be applied. After applying the correction factor N160 13.8, now we will convert this N160 to N160 CS. N160 CS for fine contents say 15%, so N160 CS is 17. So we have converted this N160 to N160 CS. Now from the curves which I have shown, from this curve, now because we have converted to clean sand, so corresponding to 17, approximate value is 0.185 from this curve. So that value, so 0.185 is CRR. Now magnitude scaling factor, because this CRR is for an earthquake of magnitude 7.5. In our problem it is given 6.75. So from the table we will see magnitude scaling factor and divide, this ratio will be multiplied by magnitude scaling factor. So answer is 0.92. This is less than 1. Therefore liquefaction is expected to occur. So this is how we calculate the liquefaction potential. Wherever we go for soil investigations, normally we find out bearing capacity. We conduct the test, then we calculate bearing capacity based on shear failure, then calculate bearing capacity based on settlement. That's all. But at the same time, liquefaction potential should also be seen, whether liquefaction is expected in that area or not. Same N values we can use for this purpose also. Then cone penetration test. Based on SPT, we can have that. Similarly, if cone penetration test is performed, when you perform cone penetration test, in the first stage only cone is penetrated. Second stage, cone plus friction jacket assembly, both they penetrate together. Mechanism, if you see in the cone penetration test, is that first only cone moves. Say let us approximately it is 40 mm. For 40 mm only cone moves. Then for next 40 mm both cone plus friction jacket assembly, both they move together. So first value you will get, that will be QC, cone penetration resistance. Second value will be cone penetration plus friction, skin friction, side friction, both combined. So if you subtract the second value, first value from the second one, you will get skin friction resistance. So skin friction load plus point load, both you can get from this. So this first we will use this QC. So QC value we have calculated. Let us say our load will be transferred up to 10 meters. So we will start the test from the ground level, say. So values which will be along the pile length, they will be used for skin friction load. Similarly, cone resistance values for base resistance. So QC values we have, we will calculate similar to earlier case. We were having NM, then NM was converted to N160. Similarly, here we convert QC to QC1N, that is CQ into QC upon PA. This PA is again 100 kPa and QC, both should have same units. This is in kPa, then this should also be in kPa. So CQ, QC upon PA. Now this CA will be calculated from this equation, PA upon sigma V0 dash raised to power N, where N is normally taken 0.5. So sigma V0 dash as earlier, effective overburden pressure kilonewton per square meter, PA 100 kPa atmospheric pressure. So CQ we will calculate, but CQ value is limited to 2 for shallow depths. If it value comes out to be more than 2, then we will take 2. The value of exponent N is dependent on the grain characteristics of the soil. The value of N ranges from 0.5 for clean sands to 1 for clays. So normally for sands 0.5. Here we have again this curve is available for calculation of CRR. We calculated QC1N. QC1N we have calculated. From QC1N again we will convert that value to QC1N CS. We will convert that to clean sand. Earlier we converted our N160 to N160 CS. Similarly, in this case, we will convert QC1N to QC1N CS. Then we will see this curve. So, how to convert QC1N CS? Actually, these are the equations we can directly use if we are not to use the curves. From the curves, these equations have been derived by approximate analysis. QC1 and CS we can see from this curve also, or we can see those values from these equations. Okay? We can calculate the values from these equations. If QC1 and CS is less than 50, this equation will be used. If it is between 50 to 160, this equation will be used. So, how to convert QC1N to QC1N CS? For conversion of QC1 and CS, CN to CS, we will multiply it with Kc. Kc is CPT correction factor. This Kc is given by this equation, 0.403 IC raised to power 4, 5.58 IC cube minus 21.63 IC square, 33.75 IC minus 17.88. This equation will give you Kc. That Kc you will use here for calculation of QC1 and CS. Now, what is this Kc? How to calculate Kc? For Kc, we need IC. IC is used in this. In this equation, IC has been used. So, we will calculate IC. IC is soil behavior type index. This soil behavior type index we will calculate using this equation, 3.47 minus log Q plus 1.22 log F whole square and whole raised to power 0.5, where Q is normalized correction resistance. This will be calculated using this equation. QC QC value known to you, sigma V0 known to you, total overburden. This is effective overburden sigma V0 dash, PA atmospheric pressure 100 kPa raised to power n, and in this you have used Q and F also. F will be Fs over QC minus sigma V0 into 100. Now this Fs, from where this Fs will come? Again from cone penetration test. Cone penetration test, I told you, first penetration, that will give you QC. Then both friction jacket assembly plus cone, they will move in the second stage. Difference of the two values, that will give you skin resistance. From that you will calculate, difference will give you Fs. So Fs will be used in this equation. Now you will calculate F from this. QC is known, sigma V0 known, Fs is known, all parameters are known. Now you have Q and F value, substitute Q and F value in this. So you will get IC. Once you get IC, then if IC is more than 1.64, then this equation is used. If IC is less than 1.64, then Kc is simply taken 1. So substitute Kc value in this, you will get QC1 and Cs. Once you have QC1 and Cs, then from the curves or using equations, you can calculate CRR. CRR you can calculate. CSR, same equation which we have used earlier. CSR you will use same equation. This equation, CSR will be calculated using the same equation. CRR from cone penetration test, from these curves, we will get CRR. Then similarly, CRR divided by CSR, that will be factor of safety. If factor of safety is less than 1, then liquefaction is expected to take place. If it is more than 1, then liquefaction is not expected. Okay. There are some correlations also between static cone penetration and N160, QC1 and N160. If you perform one test in the other value, you can get some correlations. Some people, they have given some correlations like this, N160 and QC1 and values, some correlations are given. Now evaluating the liquefaction potential by shear wave velocity. Another method is by shear wave velocity. Normally standard penetration test, here we normally perform standard penetration test or cone penetration test. Sometimes shear wave velocity test is also performed. Shear wave velocities are determined in site using low strain measurement schemes such as seismic refraction, downhole or cross-hole surveys. The limitation of the method is that the liquefaction phenomena is a large strain event. Yeah. Whereas these tests which we are performing, they are low strain measurements, based on low strain measurements, whereas earthquake is large strain event. So error will be there definitely. So that's why not very popular method. Normalized shear wave velocity Vs1. Normalized shear wave velocity Vs1 is obtained from the field measured shear wave velocity Vs by this equation. As earlier, similar steps are there. So we have Vs. Originally we were having Nm. We converted to N160. Then N160 Cs. Similarly, Vs, shear wave velocity from the shear wave test in the field, then converted to Vs1 by this equation, Pa upon sigma 0 dash raised to power 0.25. So CRR 7.5. So that will be applicable to cone penetration test also, that those curves, they are for 7.5 magnitude earthquake. So if your expected earthquake is of different magnitude, so it will be value will be multiplied with MSF, magnitude scaling factor. So similarly, this equation is for CRR 7.5. A Vs1 upon 100 plus B Vs1C minus Vs1 minus B upon Vs1C, where Vs1c is critical value of Vs1, which separates contractive and dilative behavior. A and B, they are curve fitting parameters having values 0.022 and 2.8 respectively. So A and B values have been recommended by researchers like this for 7.5 magnitude earthquakes. And Vs1c critical values we can take approximately from this. So now rest is same, then you can calculate factor of safety against liquefaction as earlier. So these three methods for sand. Liquefaction of clay soils. Clay soils would be considered liquefiable if all the following criteria are met. Weight of soil particles finer than 0.005 mm is less than 15% of the dry weight of soil. Second is liquid limit by Atterwork tests of the soil less than 35%. Moisture content of the soil less than 0.9 times the liquid limit. Clay soils not meeting all of these criteria may be considered to be non-liquefiable. So normally that liquefaction problem is faced in loose or medium sands. Now we will talk about earthquake induced settlements. Tendency of sands to densify when subjected to earthquake shaking. That is well documented. Subsurface densification is manifested at the ground surface in the form of settlement. Earthquake-induced settlement frequently causes distress to structures supported on shallow foundations, damage to utilities that serve pile-supported structures, and damage to lifelines that are commonly buried at shallow depths. Dry sands, now earthquake-induced settlement for dry sands. Dry sands densify very quickly. Settlement of dry sand deposit is usually complete by the end of an earthquake. And settlement of saturated sand deposit requires more time. Settlement can occur only as earthquake-induced pore pressures dissipate, because immediately due to earthquake there will be sudden increase in pore water pressures. So that depends upon drains provided, length of drain, if there is dissipation of earth pressure in small time, then settlement will be in small time. Otherwise settlement will take more time. Time required for this settlement to occur depend on permeability and compressibility of the soil and on the length of the drainage path. It can range from a few minutes up to about a day. Now, estimation of earthquake-induced settlements of sands is difficult. Errors of 25 to 50% are common in static settlement predictions. So even less accuracy should be expected for more complicated case of seismic loading. So settlement calculation definitely will have great errors. Now earthquake-induced settlements in dry sands. Densification of dry sands subjected to earthquake loading, that depends on the density of the sand, amplitude of cyclic shear strain induced in the sand, and number of cycles of shear strain applied during the earthquake. It will depend on these factors: density of sand, amplitude of cyclic shear strain, and number of cycles of shear strain applied. So at any given depth, effective shear strain, gamma effective, may be estimated by this relation. Gamma effective is, what is gamma effective? Effective shear strain. So shear strain, what is tau average? Average cyclic shear stress. Stress upon strain is modulus. So G effective is effective shear modulus. So tau average upon shear modulus, that is shear strain. So gamma effective is tau average upon G effective. So this is shear stress and this is shear modulus. You will get shear strain. Tau average over G effective. We can write it like this, dividing numerator and denominator with G max. G max is shear modulus at low strain level. G max is shear modulus at low strain level. So we will write it G max. We have introduced G max in this because curves which are available, they are in terms of that. So tau average upon G effective is this, by definition, gamma effective shear strain. You can write it like this: tau average upon G max divided by G effective upon G max. Okay. Now tau average you can calculate from this equation: 0.65 A max upon G sigma V0 RD. All terms we have used earlier. 0.65 A max upon G. Here this A max, if earthquake expected is say 0.3 G, so then here we will write 0.3 G in this equation. G will cancel. So 0.3 and sigma V0 total overburden pressure. Sigma V0, this is actually sigma V0 dash, I think. So equation now this becomes gamma effective G effective upon G max equal to, now if we combine equation number 1 and 2, you will get max. Equation number 1 जो हमने लिखी, this equation, from this equation we will get gamma effective G effective, you will get. Here sigma V0 and G max, they should have same units. Now G max can be calculated by the geotechnical engineering. This equation will give you answer in pounds per square feet. G max you can calculate from this equation. This actually 20,000 if used, answer will be in pounds per square feet. Now having computed gamma effective, G effective on G max, now curves can be used. Curves are available, these curves are there. Corresponding to that you can calculate gamma effective. Effective shear strain you can calculate from this. So directly from definition you will not be able to get of effective shear strain. First we have calculated this gamma effective G effective on G max. Then whatever sigma m dash value you have, you will select that curve. Corresponding to that you can calculate this gamma effective strain. Knowing effective cyclic shear strain gamma effective from those curves, volumetric strain epsilon c can be estimated by using another set of curves given by Tokimatsu and Seed in 1987. Available from these curves, cyclic shear strain, and on other side we have volumetric strain. Cyclic shear strain you have then you can use this set of curves. If you have n values, then you can have this set of curves. If you have performed SPT in that area, n value you are having, then you can select, let us Gamma effective is this gamma cyclic. From this you can calculate this value. This will be gamma epsilon C. Epsilon C is volumetric strain. From this volumetric strain you can calculate, because all those curves they are for an earthquake of magnitude 7.5. So if your area earthquake expected is different from that, then your epsilon C value which you have calculated, following the experimental results of Pike et al. 1975, the effect of multidirectional shaking is accounted for by doubling epsilon C. If we are to count for, then whatever value we have obtained from those curves, we will double that value. We will multiply it with 2. So epsilon C which you have calculated, we will multiply it with 2. So to actual we will consider as 2 into epsilon C. So amount of settlement due to earthquake shaking may then be obtained by multiplying the corrected volumetric strain by the thickness of the sand layer. For if let us say sand layer thickness is 2 meters, 3 meters, whatever, so we will multiply with that. Similarly, one example I have given, settlement of say 15-meter thick deposit of loose sand with an average corrected SPT resistance of 9 was estimated for an earthquake of magnitude 6.75 by Takematsu and Seed. Maximum ground acceleration is expected to be 0.35 g. Let us say this data is there. Then what we will do, we have different sand layers, say first layer 3 meters, different layers. Okay. So gamma of different layers, then N160 for different layers. Here I have taken 9 only, but for this layer it may be 9, for this layer may be 11, 12, 15, different values of N may be there. So we will calculate sigma m dash or sigma 0 at the center of each layer. At the center of each layer we will calculate gamma into Z, effective overburden pressure. G max will be calculated using the equation 20,000 N160 raised to power 1 by 3 sigma m dash raised to power 1 by 2. So we will calculate G max. Now after calculating G max, gamma effective, G effective upon G max. This we can calculate as we have written, equation number 2 we have written. So from that we will calculate. Then gamma effective we will calculate from the set of curves, first set of curves जो मैंने आपको अभी these curves. Gamma effective, G effective upon G max you will calculate, from that corresponding to the curve, your curve selected based on sigma m dash, you can calculate this gamma effective. So gamma effective from that figure, then epsilon C from the next set of curves corresponding to gamma, you can calculate epsilon C. Epsilon C for that will be for an earthquake of magnitude 7.5. Then epsilon C for our case magnitude, we will multiply it with 0.85. Then it will become corresponding to earthquake of magnitude 6.75. Then Pike et al. Recommendation to consider multidirectional effect, we will double the value. So this epsilon C will be multiplied by 2. Then settlement will be thickness multiplied by this value. Okay. So total settlement, if you have considered all the layers, then you will add up all, that will be total settlement. Another approach is Takematsu and Seed approach, post-earthquake densification of saturated sand, that is influenced by density of, that was for dry sand. Now for saturated sand, maximum shear strain induced in the sand and the amount of excess core pressure generated by the earthquake, laboratory experiments have shown that the volumetric strain after liquefaction varies with relative density and maximum shear strain. Takematsu and Seed used correlation between N160 and relative density and an estimate of shear strain potential of liquefied soil from N160 and cyclic stress ratio to produce chart that allows the volumetric strain after liquefaction in M7.5 magnitude earthquake to be estimated directly from cyclic stress ratio and SPT resistance. For earthquakes of other magnitudes, equivalent stress ratio can be determined. These curves have been provided. We will perform SPT as earlier. From SPT data N160 you have. Corresponding to N160, you can calculate CSR M7.5, CSR M7.5 and N160, and corresponding to that, wherever your point falls, you can calculate volumetric strain. Clear? N160, you have performed SPT, you have N160, you have CSR M7.5 as we have calculated earlier, liquefaction potential based on SPT. CSR M7.5 you have calculated value, N160 you have value corresponding to these two. Suppose your point lies here. So approximately we can calculate volumetric strain. So that volumetric strain multiplied by thickness of sand layer, that will give you settlement. Similarly, one example, let us suppose this 10-meter loose sand layer is there. If we are to calculate for 2 to 4 meters, let us say n value is 6, then next 4 to 6 meters n value 7, 6 to 8 meters we have different n values, then we will calculate N160. These n values are measured n values, nm which I have written. So then multiply with correction factors N160, then you will calculate CSR. Then from the curves corresponding to N160 and CSR, these curves corresponding to N160 and CSR, you can calculate epsilon C. Then multiplying with thickness of clay layer, thickness of sand layer, you can calculate settlement. Similarly, now another approach is Ishihara and Yoshimin approach. They have also given some curves which are used to calculate post-liquefaction volumetric strain. Settlement will be layer thickness into strain. These set of curves they have developed. Post-liquefaction volumetric strain and factor of safety which you have calculated. Factor of safety, and these curves are for N120, QC1, 110. If you have performed SPT, you have N values. If you have performed cone penetration test, you have QC values. Accordingly, you will select the curve. Factor of safety you have calculated. Factor of safety and corresponding curve, whatever value you will get, that will be post-liquefaction volumetric strain. So post-liquefaction volumetric strain multiplied by thickness, that will give you settlement. So these are some methods for liquefaction induced settlements, and I have talked about some methods for liquefaction potential calculation. That's all from my side. Okay. Now, if you have any question. Yes, sir. Normally these are for earthquake related, all these corrections are applied. Otherwise we apply two corrections to SPT values. Liquefaction for overburden correction and dilatancy correction. Only two corrections normally we apply. But for earthquake purpose, well, if you are to calculate liquefaction potential, then we need to apply all these corrections.
Because you are correcting for N60, you also need an energy measurement for the SPT. Right?
That correction has been applied only because with that correction.
Because without energy measurement, you cannot calibrate it to N60.
No, no. Actually, energy measurement.
Yes, energy measurement is required. Otherwise, because either way, suppose SPT is being done in the field with the
Yeah.
automatic,
Uh,
and transfer will be more than 60. Or it is
huh?
being done by the manual method, it will be less than 60.
That.
So in that case, we need energy measurement.
So see, it is not necessary that 100%, 60% you will get.
It is calibrated for 60.
Some approximation is always there. Actually, in dynamics, so many approximations are there. I already told you that results, we can't say they are error free. These are all based on experiments. Most of these curves, they are based on experiments, not scientific theory. Sir?
We can do, sorry, I'm losing my voice. We can do one thing. Pick SPT profile from any one site, or even make one up. Yeah? Estimate um, the liquefaction potential and settlement from that. You also mentioned you can convert the SPT into QC, the correlations.
Yes, sir.
Use those correlations, get the QC, and do the same calculation again. Use the VS correlation and get the settlement by that method. Then you can see what is the error band by doing that. Maybe we should set it as a
actually those correlations,
for the students.
but those correlations, they are also based on experiments.
Yeah, but what is the error in the correlation? That's what you will get.
But
so
error,
one method gives 1 meter settlement, the other one gives half a meter.
then I think, sir, we should not use correlation. We should perform both the tests. Then we can compare.
Yeah,
If we compare the results with the correlations, both the tests we perform, only then some error will be detected. If we use only correlations for calculation of QC from n value, then error will not be detected, na, because that is based on n value only.
But
so if we perform both the tests,
I don't think.
and then answer will not be same, because that is a great approximation will be there. Actually, these methods are very approximate methods, very approximate methods.
In SPD, there are more corrections.
Yes.
CPT is why that's why we prefer CPT because
Actually, energy measurement is rarely done in the field.
SPD is that should not be.
Correct.
Actually, in India, mostly people depend on SPD.
SPT code of India nowadays specify the energy measurement. Recently released.
Yes.
Graph of calculating shear strain effective with respect to shear strain effective G effective by G. In this
one?
Yeah. In this graph, that 15 cycle is mentioned. What is it is what is that, sir? 15 cycles of that.
15 cycles of.
If there are 10 cycles, 20 cycles,
Then this is for 15 cycles.
This is for 15
These curves are for 15 cycles. No other calls are available. Only they people Takimatsu seed, the seed eater, only two three.
It's done in 87,
Yes,
and that's the only link we have to get the second.
yes. There actually most of people they have not worked on this. Very few people. Takimatsu seed eater. You will see same names will be there.
You look at it, it's Tokimatsu, not Takamatsu.
Tokimatsu.
Tokimatsu. Koji. K-O-H-J-I.
In so must
First
be
name, Tokimatsu.
okay.
So,
It
yes,
is
yes.
it is
Yeah, that is
Tokimatsu.
that. I think he's the last to see after the seed died.
It's a seed died.
After the this supervisor.
Okay, thank you.
Okay.
Then tomorrow at 9:30. Huh?